The following presentation gives an overview of Exareme and the system main features. More and more applications face the need to perform ad hoc processing on large datasets like complex analytics, ETL transformations, and machine learning algorithms. The process can be described by data-intensive workflows or for short data flows. The data flows can be expressed using either high-level APIs or languages and are executed on highly parallel systems like Hadoop, Spark, and Tez. Towards that direction, we have created Exareme, a system for elastic large-scale data processing on the cloud. Exareme exploits the elastic properties of cloud infrastructures. It can dynamically change the size of the allocated infrastructure and express trade-offs between execution time and monetary cost. Exareme uses SQL to declaratively describe query computations. We have also introduced a new language called ExaDFL. ExaDFL is based on SQL but extended to capture parallelism. It provides high productivity in expressing and fine-tuning complex data flows. User-defined functions or UDFs are an integral part of our new language and allow us to perform complex computations. Our processing engine uses just-in-time compilation and fusion techniques to blend UDFs with relational operators in order to accelerate performance. Let's now look at the building blocks of Exareme. The master node is the main entry point to the system and is responsible for the coordination of every other component. The master node contains the gateway through which the user connects to the system, the query optimizer that determines the most efficient way to distribute the execution of a query, the scheduler that translates the query plan produced by the query optimizer into Exareme's execution plans by assigning operators to workers, the execution engine that is responsible for scheduling the operators of a query by taking into account the dependencies as they are captured by the execution plan and the available resources of worker nodes. The execution engine also monitors the execution of data flows and handles possible failures. Finally, the workers execute the query operators and transfer intermediate results. From a user's point of view, Exareme can be used as a traditional database system. Queries are issued to the system and results are retrieved. When the system receives a query, it is passed on to the parser that creates its corresponding relational algebra expression. Then the query optimizer transforms it into the optimal ExaDFL query, and finally, the scheduler creates the execution plan. The execution plans that Exareme executes can be represented as directed acyclic graphs, the nodes of which represent arbitrary computations and the edges denote producer-consumer dependencies. The execution plan is evaluated on the worker nodes by a processing engine. Finally, the query output is returned to the user. The processing engine of each worker is a system called MADIS. MADIS is responsible for executing the computation as described by the SQL part of ExaDFL. MADIS is an extension of SQLite that provides a highly expressive mechanism of writing UDFs in Python, a large collection of UDF libraries that can perform data analysis, text or data mining, data cleaning, stream processing, and integration of external sources, and many more. MADIS performs UDF fusion to minimize context switches between the relational query and the UDF evaluation. It also applies just-in-time compilation to speed up UDFs by compiling execution traces. Exareme supports two languages at different levels of abstraction. The first language, SQL, can be used to declaratively describe computations. The second language the system offers is called ExaDFL. It is based on SQL but extended with data parallelism primitives and UDF support. ExaDFL enables the user to determine the parallelism level and type for every SQL computation. Direct usage of SQL is recommended only for the users familiar with ExaDFL and database concepts. Queries issued to the system can be expressed using either language. ExaDFL employs some carefully selected parallelism primitives in order to describe the parallelism needed for each query. These primitives are divided into input and output. Let's first discuss the input primitives. These describe how the input tables of SQL operations are combined. The direct primitive is used when the input tables are partitioned in a convenient way in respect to the SQL operation that is performed on them. For example, when performing a join between two tables, a convenient partitioning scheme is to have the input tables split in the same amount of partition and on the joining attribute, or if one of the two tables is replicated. The Cartesian product primitive creates all the possible combinations between the input tables. It is useful when the partitioning of the input tables is not done in a convenient way in respect to the processing that is performed. The tree primitive performs a multi-level tree reduction on a single table, generalizing the two-level combine-reduce reduction of MapReduce. This is used for aggregate operations. Let's now look at the output primitives that the Exareme system offers. Using the same output primitive, the output partitions follow the partitioning scheme of the input. The partition primitive lets the user specify a new partitioning scheme. Finally, the broadcast primitive replicates the output to as many workers as the user specifies. Let's now use an example to demonstrate the use of Exareme. Suppose that we have two tables, order and customers. We want to find the name of each customer that has placed an order. In our first example, let's assume our data is not distributed and are located in the same node. We need to perform a join between the two tables, customers and orders, on the customer ID column. The syntax of the corresponding query can be seen on the left. We are performing a natural join between the tables on the order ID column. Let's now perform the same query when the two tables are partitioned and distributed to multiple nodes. The tables are split to three partitions based on the value of the customer ID column. We can use Exadfl to perform the join of these two tables. Exadfl is comprised of two distinct parts. The first part, highlighted in yellow, describes the parallelism, and the second part, highlighted in red, describes the computations that each worker is going to perform. Since the two tables are partitioned in a convenient way in respect to our query, we can use the direct primitive to instruct Exareme to perform the join locally in each worker. This operation produces the correct result since the partitioning is done on the joining attribute and each table has the same amount of partitions. If we had used the Cartesian product primitive, which is Exareme default behavior, we would have created all the possible pairs between the partitions of the two tables and performed the join operation on them. The result table would have been the same. The Cartesian product will produce the correct result in every case, but when the direct primitive can be used, it provides performance benefits. Let's now look at the output primitive used. The same primitive, which is Exareme default behavior, will not change the partitioning scheme and will produce an output table with three partitions. By using the broadcast primitive, the output table will now be replicated to three workers. In this example, we will go through the execution cycle of a query. The query we're using performs a join between the orders and customers table. The SQL query is translated into its corresponding algebraic expression by the parser and translator. Then, the optimizer creates the Exadfl query by deciding the level of distribution and applying optimizations. Finally, the scheduler creates the execution plan by assigning the operators that are described in the Exadfl query to workers and capturing their dependencies. Finally, the execution plan is passed on to the execution engine that coordinates the workers that execute it. In our final example, we'll see how Exareme handles the federation of external data sources. Exareme provides a way to create specialized mappings that allow access to external tables without modifying the SQL syntax. The query optimizer is responsible for recognizing the external sources and federating them into our system. Suppose that Exareme needs to access two external endpoints of the storage cloud. The first endpoint is Northwind, that contains the table customers, and the second endpoint is Northstream, that contains the table orders. By defining mappings between endpoints and aliases, ext A for Northwind and ext B for Northstream, Exareme knows where to find an external table that is referred by its alias. Therefore, when submitting an SQL query using these aliases, the query optimizer understands, by reading the mappings, that table XA customers is located in the northwind endpoint and table XB orders is located in the north stream endpoint. Thank you.